Now let's talk about magnetic field.
A magnetic field is the area around a magnet, magnetic field, or an electric charge in which magnetic force is exerted. Magnetism. It is a phenomenon associated with magnetic fields. It arises from the motion of electric charges. Types of magnetic materials. Soft magnetic materials easily magnetized and tend to lose their magnetism easily. Hard magnetic materials are difficult to magnetize and tend to retain their magnetism. Types of magnetic materials. Diamagnetic substances, slightly repelled by a magnetic field, do not retain the magnetic properties when the external field is removed. Paramagnetic substances, slightly attracted by a magnetic field, do not retain the magnetic properties when the external field is removed. Ferromagnetic substances exhibit a strong attraction to magnetic fields and are able to retain their magnetic properties after the external field has been removed. Lorentz force. The Lorentz force is the force on a charged particle due to electric and magnetic fields. Magnetic force. Right-hand rule. The thumb is the direction of the motion, pointing finger, direction of magnetic field, and the middle finger is the direction of force. Motion of a charged particle. Uniform circular motion. A negatively charged particle moves in the plane of the paper in a region where the magnetic field is perpendicular to the paper. The magnetic force is perpendicular to the velocity, so the velocity changes in direction, but not magnitude. The result is uniform circular motion.
And now let's talk about Lorentz force. Lorentz force is the force exerted on a charged particle Q moving with velocity v through an electric field E and magnetic field B. The entire electromagnetic force F on the charged particle is called the Lorentz force. After the Dutch physicist Hendrik A. Lorentz, and is given by F is equals to QE plus QV times B.
The Lorentz force is a phenomenon experienced by an electric current which is made up of negative charged particles or electrons moving through a wire. Shown here as yellow particles, electrons move from negative to positive. However, the convention is to think of electrical current as moving from positive to negative. So that's how we'll show it here using red particles. If it's not moving, a charged particle doesn't create any magnetic field. But when it moves, it generates a little magnetic field around it, shown by these green arrows. Flip the direction of the current, and you flip the direction in which the magnetic field circles around it. The magnetic field produced by the current will interact with another magnetic field just the way two magnets repel or attract each other. Here's a horseshoe magnet with a north and south pole. The magnetic field always points from north to south, shown by the blue lines. This wire is arranged in a kind of pendulum so we can swing back and forth. Let's insert the horseshoe magnet into the setup and see what happens when electricity runs through the wire and creates a magnetic field around it. The pendulum swings in a different direction perpendicular to the horseshoe magnet's field and to the movement of the current. If we reverse the direction of the current, the magnetic field that generates will turn into the opposite direction, causing in turn the pendulum to swing in the opposite direction. Flipping the horseshoe magnet around to reverse a magnetic field around the pendulum will also cause the wire to swing in the opposite direction. The Lorentz force is what makes our electric motors work. Without this force, our modern world will be quite different.
Hi, my name is Philip, and I am going to explain the motor effect and how we can predict if the motion or the movement of a charged particle in a magnetic field. As you probably remember, all around magnets comes a magnetic field that like poles repel and opposite poles attract. Now imagine a wire going through a magnetic field. Now we run a current from positive to negative to that wire, and that wire will experience a force, meaning that wire will move. And that effect is really important because we use loads of this effect in different devices. This is called the motor effect. Now, how did I know that the wire is moving upwards, not down, not right, but upwards? To work that out, we can use something called Fleming's left-hand rule. All you have to do is to make this shape with your finger. The index finger pointing forward, middle finger pointing to the right, and the thumb upwards, pointing upwards. Each of those fingers represents a different thing. The index finger represents the direction of the magnetic field. The middle finger represents the direction of the current, and the thumb represents the direction of the movement of the wire. So what we have to do is to line up those two things that we know with your hand and see which direction the other finger is pointing to.
In this example, the magnetic field is going to the right, from left to right, and the direction of the current is going to the outside of the page, meaning if we line up those fingers to the direction of the current and the magnetic field, we get the thumb that is going upwards. That is the direction of the movement of the wire. So let's have another example. So the direction of the magnetic field is from left to right, and the direction of the current is from up to down or downwards. So the direction of the movement or the direction of the movement of the wire is to the person or to you or outside of the page.
Now in this other example, imagine a dart going to you and a dart going away from you. If a dart is going towards you, you can see a circle with a dot in the center. If it's going away from you, you can see the back part of the dart and you can see across. The direction of the current is represented by these two. In this example, the current is pointing right at you and the magnetic field is pointing downward, meaning the movement of the particle of the wire is going to the right.
Hi, this is Nick, and I am going to discuss the force in the current carrying wires. The basic idea is that we're given a segment of wire of length L carrying current I and a magnetic field P, and we have to find the force in that wire, the magnetic force in that wire. There are two expressions that we use for this. The first one, we have FP is equal to IL cross B in this expression. I is the current, L is the length of the wire, segment P is the magnetic field, and then F sub B is a magnetic force. And the only tricky thing about this is that the L term is actually a vector. You notice that it has the arrow on top, and we choose the direction of L to be in the positive direction of the current. Now, the L cross B is just a vector cross product. So it's also possible to write this in terms of the magnitude, in which case we would have FB is equal to ILB sine theta. And again, I is the current, L is the length of the wire, segment P is the magnetic field, and FB is the magnetic force. So the only new thing if we're going to use the second equation in terms of magnitude is that we have to think about what the angle theta is, and the theta is this angle between vectors L and B. And the theta is the angle between vectors L and B. And you can use either of these expressions depending on your preference. I'm not going to go into the proof for this right now. It's not a very difficult proof, but I don't want to take up your time with that. Alright, let's look at an example. A 2.5-meter wire carries a 7 amp current in I direction, 40 degrees east of the north through a magnetic field that is 3 Teslas west. Find the magnetic force acting on the wire. We're given that the current is 7 amps. We're also given that the wire is 2.5 meters long, and we're given the magnetic field as being 3 Teslas to the west. We are also given the direction of the L vector as 40 degrees east of north. Looking at that given data, I want to actually consider which equation is going to be easier to use. So first, I'll check out I times L cross P because we have the L vector, we have the B vector. And then I'm going to also consider in terms of the magnitude, is equal to ILB sine theta. Looking at the first one, FB is equal to IL cross B. I have the L vector, I have the B vector, but it's not immediately obvious how to set up the cross product. And as with all the physics problem, I really need to do a sketch for this because of the directions are expressed with respect to the east, north, and west. I'm going to actually draw out north, east, south, and west. And I know that this is going to be a 3D problem just because these often are. So I'll have north, east, south, and west, and I've drawn it like this at an angle because the north, east, south, west are all in the horizontal plane. We also have directions down into the ground and upwards this guy. Okay, so with respect to these directions, then I need to draw this out. L is 2.5 meters, 40 degrees east of north. So that means I start north and then I go 40 degrees towards the east like that. And then I can draw my vector. So the L vector is between north and east, and it's actually 40 degrees rotated away from the north, which means that it would be 50 degrees from the east if we were to add those up because north and east should be 90 degrees apart. The next thing is to look at the magnetic field, which is to the west. Looking at the diagram, it's easier for me to use the second form of the equation because I know the current, I know the length, and I know the magnetic field. So the only unknown is the angle between them. Now, the angle between them. Remember, it's really tempting when you see a problem like this to just take what angle was given. In this case, we were given 40 degrees and it's tempting to pump up in the 40 degrees. And then just say, alright, I got the right answer. But unfortunately, it's actually not true. The angle that you need to use is between L and P. The angle 40 degrees is between L and north. So this angle theta is actually equal to the 90 degrees, which is between west and north, plus 40 degrees. So the theta is actually equal to 130 degrees. So I substitute that in 130 degrees and I'm just using red here. I know it violates my color coding, but I'm using red to make it more visible. Then I can solve for this. I know all of those things and I'll find out that the magnetic force has a magnitude of 40.2 newtons. Now, this is great. A lot of students at this point say, yes, I have the answer. I'm done. And unfortunately, physics teachers, as I'm sure you are, are a little bit more picky and they might just be picking up to say, hey, there's a vector on top of that. Force is a vector, so it has a magnitude and direction. Now, If we're using the second form of this equation, we need to actually use the right-hand rule to get direction. If we use the first form, I-L cross B, then the direction comes out of it. But we had to express L and by using vector notation, typically using unit vector notation. And then, the unit vector notation that results from that gives you the direction of f of b. In this case, we use the right-hand rule. So to start using the right-hand rule, we have our fingers along plus L. Then we curl those fingers without moving our palm towards B. And the direction of our thumb is pointing gives the rough direction of f of B and B because it's a cross product has to be perpendicular. And the direction of our thumb is pointing gives the rough direction of f of B and B because it's a cross product has to be perpendicular to both A and B. So in this case, your thumb is pointing up, FP is up. Therefore, FB as a force is equal to 40 newtons up. And that's our final answer.
So now, let's talk about Biot-Savart law. Yes, Biot-Savart, because it is pronounced in French. Biot and Savart, the two Frenchmen who are scientists, conducted experiments on the force exerted by an electric current on a nearby magnet. They arrived at a mathematical expression that gives the magnetic field at some point in space due to a current. Biot-Savart law calculates the vector magnetic field, which is dB, due to an infinitesimal length of current, so that is the dB. The total vector field B can be found by integrating over the total length of all currents. So dB is equal to mu sub 0 times I over 4 pi times dl times r cap over r squared. So as you can see at the picture below, so the I represents the current flow of the wire. So dl represents the infinitesimal length current. The angle of the two, dl and r, is called theta. So here we can see a wire on the hand. So the I represents the current, and it is parallel to your thumb. So B represents the magnetic field, and the fingers that wraps around the wire is the magnetic field. So let's talk about the equation of Biot-Savart. So imagine a wire, a curved wire or a straight wire, it doesn't matter. So we want to find magnetic field in some point in space separated from that wire, so that's letter B up there. The DS part here stands for a line segment, and notice that all line segments are the same in length but could point in any direction. R squared, on the other hand, represents the distance, specifically the distance from length segment to the point P, and each different line segment may have different distance from the segment to point P. The r hat is a radial direction, and the hat lets us know that it is a unit vector. It just exactly points the direction of the magnetic field. The integral sums up the contributions overall of these different line segments, and that will be our overall magnetic field at our point P in space. Now, let's take a look at the equation from the standpoint of units. The mu naught had a constant of Tesla meter per amperes. I, which is the current we know, has unit of amps, and 4 pi doesn't have any units. The ds part of our integral has units of meters, while the r squared part has meters squared. And our r hat, you may think it is meter, but it's not. It's a unit vector, so again, it has no units. So once we've collected these all together, what we see is 2 amperes at the bottom. So let's cancel them out. There are 3 meters, so let's cancel them also. So everything from our right hand side, all we've got left is Tesla, which the unit I expected for the magnetic field. So that's it, guys. So every time we've got a current carrying wire, we gotta end up having units of Tesla. That's all. Thank you.
Ampere's law. It is discovered by Andre Marie Ampere in year 1826, so when charges flow, they create a magnetic field, and that's Ampere's law. This is done with what is called right-hand rule.
Right-hand rule states that if the right thumb points in the direction of the current, then the finger curls in the direction of the field.
Example, a current is coming out of the screen towards you. What is the direction of the B field above this flow?
To solve this problem, we need a way of representing current going out and into the screen, and this is done with this symbol.
Think of the dot at the tip of an arrow coming at you, and think of the X as the quills of an arrow as it is leaving you. As you can see that there is space in the thumb as current coming out of the page. And the finger curl there determines the direction of the field. The magnetic field strength or magnitude produced by a long straight current carrying wire is found by experiment to be B is equals to mu naught I over 2 pi r. Mu naught, or the permeability free space, with a constant value of 4 pi times 10 to the power of negative 7 Tesla times meter per ampere, and r is the distance between the wire and some points based where the magnetic field, and I is the current measured in amps.
Here is the first example.
Find the current in a long straight wire that will produce a magnetic field twice the strength of the Earth at a distance of 5.0 cm from the wire. Note that the Earth field is equal to 5.0 times 10 to the power of negative 5 Tesla, and so B is taken to be 1.0 times 10 to the power of negative 4 Tesla due to the wire with the given equation of B equals to mu naught I over 2 pi r. The equation can be used to find I since all other quantities are known. Solving for I and entering known values gives 25 ampere. Note that the answer is stated only 2 digits since the Earth field is specified to only 2 digits in this example.